feel free to speak up and ask questions. Totally informal here. So, all right, the talk about evading AV with Covenant C2. Um, this is definitely going to be more sort of specifics about um, AMZ and AVs in general, and then we're just going to touch on Covenant and just give kind of an intro to that. So it's not so much about Covenant so much. So we'll get into that. Myself, Rob Noth, 9 years research and development at the National Security Agency, doing mostly comp sci stuff. So developing, making web apps, making native applications, things like that. And then at Level Effect, I'm the co-founder and architect of Recon, our security platform product, and Foundry, our training platform. So let's get into the substance here. So let's talk about antivirus first. Antivirus, and I picked this nice seasonal photo here because this is what I think of when I think of antivirus. I've been around antivirus for a long time. I've not only researched how it works and how it does its job at detecting things, but I've also been on the other side of it in figuring out ways to get around AV and bypassing the detection techniques that they use. So, AVs are easy to pick on because they're pretty much as old as the internet. 1971 was the technical first virus, which wasn't really a virus. It was a guy, an ARPANET, who was basically tampering around with writing a self-replicating program, technically a worm, but that didn't exist at the time. So he ended up writing the first worm that replicated itself across ARPANET. And then subsequently, the first antivirus was the program written right after that to remove that self-replicating program. So that was technically the first virus and antivirus back in 1971. Obviously, things have grown much more since then, but that wasn't even a signature-based antivirus. It explicitly knew what to remove. So let's move into kind of how more modern AVs work, where we're getting into signature-based antivirus mechanisms and heuristic and quote-unquote AI stuff. So signature-based stuff is much like what we see in this picture, just cookie cutter and template looking, very specific and static templates and things that the antivirus is looking for specifically. So what's wrong with this methodology, right? Why is it not keeping up? According to avtest.org, which is an independent third party that does research on new malware strains and variants, just this past month in September had over 12.5 million new malware cases in 1 month. So you can obviously see how that doesn't scale well when it comes to signatures. You need obviously computers to come up with signatures. You need as many humans as you can get to help filter those and avoid false positives. And you're just never going to catch that train. It's already gone. However, and maybe sadly, maybe not, most AV engines and even EDRs still have a component in them that uses signature-based detection. In a lot of cases, because it still works in some instances, there's a lot of just known malware out there that doesn't really change. It doesn't have any variability to it. So, signature stuff technically still works in those instances. But just because it works doesn't mean it's catching, 95% of malware that's out there. It's maybe down in the 10% range. So kind of the answer to signature-based failures was heuristics, and coming up with a way to have basically a chain of signatures together is what a heuristic is. More smarter solutions like EDRs and stuff have a different approach, which we'll get to in a second. But a heuristic in the AV sense, antivirus sense, is just a chain of cookie cutter templates put together. So that does allow you to have more data points. So you can have multiple things to catch something on based on either components in the binary or potentially functions that are in the binary that run in a certain way. That's also a heuristic, like a behavioral heuristic. But again, the downside to heuristics is it's still looking at known behaviors, stuff that a researcher wrote and built the heuristic based on stuff that they've seen, research they've done. Obviously, based on malware, they dissected and figured out, okay, this malware does this A, B, and C step. Let's make that into a heuristic because no other binary does that. So we can uniquely identify and isolate this binary based on those steps. It is more effective, and it doesn't necessarily require as many signature updates, because if the golden grail of heuristic building is having the ability to write a heuristic that matches, many, hopefully, malware chains or malware families. And then that way your one heuristic is going to catch a lot of things. So for example, what would fall into here, and we're going kind of down the technical track, so please ask questions if I go too deep here. But for example, like injecting a DLL into another process could be a sample heuristic that most legitimate software is not going to do. However, there are definitely still some software applications that do legitimately use that technique to do certain things like debugging, or in anti-cheat game engines, some of those things will inject DLLs into processes and things like that. So it's not foolproof, and it still requires like a human interaction to say, no, this is a false positive. It's not malware. The other problem with heuristics is it's pretty heavyweight. It requires a little bit more scrutiny. It requires watching a process potentially execute, scanning deeper into the binary, which requires more compute power, more memory, et cetera. So, you can see how it would be not necessarily worse than a signature-based engine, because a signature-based engine is going to be scanning every single file on the file system basically as many times as you want it to. So if you remember back in the day, if you're that old, you'll remember running like an old Norton antivirus scan, and it took maybe if you had a bunch of files on your 1 gigabyte hard drive, it could take an hour to scan through all the files, because it was just literally looking at everything. These days it's a little bit faster, but it still is the same problem. You have finite resources, and other applications that are running now, like Chrome, browsers are using up a lot more memory and compute these days. So that's less for these AV engines to take up, and it's more noticeable when they do take up that stuff. Your computer slows down, and can interact with or interfere with what you're doing. The other kind of downside to these other newer engines, and maybe just another kind of point of reference, is that they still rely on just some basic signatures, like I said, because they still work in some cases, especially for the older variants that are out there. Oops. All right, so EDR, I mentioned it earlier, but this is sort of the next evolution of just malware detection, antivirus, in the next stage. So EDR detection and enterprise detection response, which is what EDR stands for, is a much more enterprisey solution. It's they tend to kind of be an all-in-one, in-the-box situation or deal, where they'll come with an application, it talks to the cloud and does updates and syncs up and things like that. And then it also has like a human component where the remediation step comes in. So when something happens, a detection kicks off, it's validated and triaged, then it'll pass over to a human that works at the company, and then they'll kind of contact your IT team, your security team, and say, hey, we found this, will you let us remediate it, things like that. There's definitely different packages out there and different ways that occurs, but that's kind of the trend. That's the general sense of it. How do EDRs work? They use pretty much the same methods, using signature-based stuff and heuristics, but they also kind of tap more into the operating system. So what I mean by that is, not only are they looking at the files and how processes generally execute, they're looking for other events and other triggers to notify them of something anomalous or something different is happening, something probably malicious. So in that sense, you're getting way more data points. Like I mentioned, signature is like a one data point. A heuristic is 1 to 5 or many data points, but still probably not more than 5 or 6. And then EDR, you can have dozens of data points, depending on the heuristic and the flag that they're looking for. So the strengths are it doesn't completely rely on a signature, and it's also, as I mentioned, since it hooks into so many other places in the operating system, it's able to find things like fileless malware. It's able to find just user abuse sort of techniques where users are doing things that they're not supposed to be doing. Like an EDR can trigger on that as well. If you have kind of fine grained filters and policies set up that way, you can find DLP, which stands for data loss prevention stuff. So users removing files from the system potentially in an unauthorized way. So EDRs have a lot more going for them. They're definitely much better than the Norton antivirus of old and the old scanning engines. But again, they still do rely on known information, right? That's kind of the first weakness here. And you sort of have to understand, like, the reason why that is that they rely on this known information is because that is the quickest way to just stay up to date and find as many things that it can. So by just standing on the shoulders of other people and researchers, they're gaining all that knowledge and they build it into their product. If they're good at what they do, then they also sort of have their own research arm where they have their own internal researchers that are doing their own malware research, finding new techniques, building that into their product, and making their product even better than just what's already known out there. So some examples of these are like CrowdStrike, Sophos, Kaspersky. They have their own internal research groups that have really good researchers, former hackers, that kind of thing, that know how to play the game. So they come in and help the product get better by building these heuristics or signatures that the EDRs use. The biggest downside, I think, in my book, is that it is super expensive. EDR is very expensive because it's meant for enterprises. It's in the name, right? So this is meant for large companies, have big networks that are harder to manage. Maybe they don't have a big security team, but they have bigger budgets. So that's why they're kind of geared toward that. And because of all the other components that I just mentioned, it just makes the product itself harder to maintain and manage and more expensive to maintain and manage because you need humans in it. You need all this infrastructure. You need all this research and development to continue to make the product better and finding and relevant, at finding good stuff. Sorry, I have a typo here. Yes, enterprise instead of endpoint detection and response.
I have a question. Is Windows Defender, is that not considered like EDR?
In my book, it is, but the problem with Windows Defender is that it doesn't really have an enterprise like monitoring and response solution. So it doesn't like collect. It doesn't have a really easy way or a good way to collect all the logs in the back end and do analysis and stuff like from back at the SOC. Whereas like CrowdStrike, Carbon Black give you those like analytic tools and they let you like vacuum up all the data and do your own analysis. That's the only real difference. And I think why people kind of knock Windows Defender as far as like enterprise solutions go, but it has the same capabilities as far as detections go as, CrowdStrike or Carbon Black do. So yeah, good question. And honestly, when I kind of consult with smaller companies, I tell them just use Windows Defender because it's that good. It's really good at detecting stuff. It's already tied in with AMSI, which we're going to get into in a little bit. But it's a good solution for the smaller companies, definitely for mom and pop shops that have less than a dozen computers. they don't need to drop the money on something really expensive to have good security setup. But everything's in a layer kind of setup anyway, so you need to have as many things as you can afford to stay safe. The other kind of the last weakness to touch on with EDRs is false positives. One of the ways that EDRs mitigate false positives is sort of what I just mentioned here. Like, they vacuum up a lot of data, they provide it to you in a dashboard, and then they sort of let you figure out what's the false positive and what's the real one, right? So I wish it was better than that. Hopefully we're working towards something better than that, but that's where it stands right now. These tools can pretty much only be as good as how you have it configured and have it set up. If you don't configure and set up these tools and really baseline it to your enterprise, to your network, it's not really much better than having Windows Defender by itself running, right? Like, you're not getting the money out of it. And then the problem with that, again, falls back into the expense and the complexity. It's hard to configure them. It's difficult to set them up right. It's difficult to go back and test this stuff. Like, if you don't have an internal team that can run your own internal pen test or something to validate the rules that you're creating, how do you know that you did it right? Other than paying $1 million to have some outside firm do it. So, any other questions with EDR?
Yeah. One other question. So,
Sure.
This might be a bad question, but with something like Cobalt Strike, which when you spawn new agents or run anything with a sacrificial process, I know by default it'll spawn run DLL and inject into that, and it spawns run DLL without any arguments, which I know is extremely uncommon.
Yeah.
Is there any good reason why like something like CrowdStrike or even like Windows Defender wouldn't trigger on that? Because in my experience, I've just rarely had to change that sacrificial process, even when dealing with EDR solutions.
Yeah, good question. So, that would be one of these like false positive feedback loops that they have not followed up on and gone in and said, like, hey, why is somebody running run DLL with no flags? Like, that doesn't make any sense, let alone why is a user running run DLL on its own, right? So, yeah, and the kind of quick answer to that is, well, let me preface it by saying, like, I don't know how the internals of these EDRs work, right? Everybody's kind of different, and a lot of it's proprietary. We don't know. They're very black box to everybody that doesn't work there. So, but what I can sort of tell you and infer from that is that the engines are doing something to basically break out of the loop before it determines that this is bad. So, what I mean by that is they're looking at run DLL, the file itself, the executable. They're seeing that run DLL is signed by Microsoft, that it's legitimately signed. The date is correct. It's not expired. The hash matches probably unknown whitelist that they have. So already it's okay. It's, you're checking the boxes of safety, and then it sees no arguments, so it has no reason to follow any subsequent path, because if you normally run DLL, you're going to pass it a DLL and you're going to pass it like a function to execute right in that DLL. So when the engine runs and it sees the command line just says run DLL and there's no parameters, you're basically just like breaking it, because it's going to look for the DLL. It doesn't see a DLL, so it just says, okay, I guess this is fine, and it doesn't proceed to inspect it further. That's my hypothesis anyway. But does that answer your question, Jim?
Mm-hmm. Thanks.
Okay, cool. So let's dive a little bit deeper into signatures. What is a signature? What does it look like? It could be as simple as a file hash. We've seen these sort of, if you've done this kind of stuff before, if you've messed around with VirusTotal, or you've kind of looked at IOCs from previous reports or things like that. A file hash is simply just like a fingerprint for that file, right? It's a unique identifier that identifies that file. In my example here in the slide, you can see how I MD5 hashed the hello world with an exclamation point on the first line. And then I did it again without the exclamation point, and it's a completely different ID, right? The hash is just a mathematical algorithm that computes this ID from the data that you give it. So no matter what data you give it, it's gonna do the same computation until it, from the beginning to the end, and then give you the same length number. But if one byte is different, it should be different. You should never have what's called a collision, where you have two different pieces of data with the same hash sum, the same value here. It should always be different. So we can use this to quickly sort of just pass around this information, these IOCs, incidents of compromise. We can pass around this telltale sign of like, hey, if you see this a file that has an MD5 hash of EDO7, etc., it's bad. So immediately flag it, quarantine it, do whatever you need to do. And then we as organizations, as enterprises, as companies, or whatever, we can pass this information around in what we call threat feeds, things like that, and help each other out, basically. So that's one way to look at a signature, and that it is still used as a signature hit if it matches a file hash. But we also have byte signatures, which are the more kind of complex way of inspecting a binary if it doesn't match any known file hashes. So as I said, we can change one byte in the file. So I could, if I'm a programmer and I'm writing malware, I can insert a bunch of random bytes into my program, and that will immediately change the file hash. So basically, every time I compile my program, it will have a different file hash. So it's pretty simple to get around the file hash problem as far as AV detection goes. Byte signatures are a little bit harder because byte signatures look for specific byte codes in your binary, and you're not going to really necessarily know which binary or which bytes the AV engine is hitting on unless you see the signature, which you can find the signature once you, if you're running the AV that's catching your binary, you can usually find the signatures, and then you can try to distinguish which one is hitting on yours. You'll see the signature pop up because it'll tell you, when the antivirus pops up and says, hey, we found this Trojan dot abc dot whatever, that's the heuristic or signature name that it's hitting on. So if you can decipher what that is, then you can kind of figure out what signature is hitting on your binary. But this is an example of what it looks like. I try to color coordinate it here so you can see, at the top, that's the assembly of the binary that we're trying to catch in this example. And then in the bottom, you can see a Yara format representation of what that binary looks like, or what that signature looks like when it gets passed around in a threat feed or some other sort of sharing mechanism. I guess the important thing here to understand is that this stuff is looking at the raw code in the binary. It's not looking at a file hash. It's not looking at the program executing. It's just looking at the binary on disk, however it looks. So like a static representation, right? And then Yara, to kind of just go into that a little bit, Yara formats, it looks kind of like JSON, if you're familiar with JSON file format. It's just a way that the industry, the InfoSec industry has come up with this kind of protocol, this standard way of sharing this information using Yara rules. So there are various third-party vendor tools that consume Yara rules. If you use tools like Carbon Black and CrowdStrike and some of those other bigger ones, they allow you the opportunity to make your own Yara rules, that you can build your own filters and do all that kind of stuff. Obviously, you need to know what you're doing in order to do that. So you need to know kind of reverse engineering, some assembly, some programming, in order to be able to create your own Yara rules. But it's once you get past that initial barrier of entry, it's not that difficult to make your own Yara rules. Is that the best use of your time? Maybe, maybe not. but that's how you would do it. So heuristics. Again, I mentioned heuristics are like a stack of signatures. Um, in this example, we see rules A, B, and C that comprise the heuristic, and then that blue line in the middle is sort of the heuristic logic. So if rule A matches and rule B matches and rule C matches, but not only that, they have to be in that sequence, then the process is equal to the malware poison ivy. So up at the top, you can see in kind of English what it's doing, and then underneath you see more what closely resembles the actual signature or code that's going through the antivirus engine when it's looking for these signatures. So it's looking for an API call to move memory, so copying memory with that string in it. So it has to match that string exactly. The software classes some registry key. And then there's an API call to create a mutex that's called, close parenthesis, bang, VO, etc. So that has to match exactly. And then a third API call to get system directory. So it's very strict, right? It's not like a loosely fitted kind of regex or anything like that. It's a very it has to be very exact, case sensitive, everything like that. You can do a little bit of like regexing, and by that I mean kind of more like wildcard searches. But you're kind of opening a can of worms, because at that point you're looking at just inviting a bunch of false positives in. So that's why these have to be exact and have to be so strict. It's because they're trying to eliminate as many false positives as possible. However, if we were to go in and change the name of our mutex to something else, or randomly generate it, we would just completely break this heuristic and the AV would not catch us. Okay, so moving beyond signatures and heuristics and kind of the old school way of how AV engines do it, and some still do, let's start talking about AMSI, which stands for Anti-Malware Scan Interface. So this is a Windows thing. There's talks of maybe being able to port it to .NET Core and expand its reach to potentially other Unix systems. But for right now, it's Windows, Windows 10 especially. So what is it? What does it do? Where does it live? How does it work? In a nutshell, it's Microsoft's script scanning engine. That's really all it's meant to do, and how it works right now. If you go to the website and Microsoft's website and look up AMSI and like how it works and what it is, they talk about how it can be set up to be an interface for your application. If you write software for Windows and like a native software, you can use it to, or you can utilize AMSI to make your product more secure. And really what that's kind of marketing speak for. You can send something to AMSI, AMSI will scan it and then give you a result back. So that's what in this example Windows Defender does. It's tied into Microsoft, so they work closely together. But as we can see, there's kind of various ways that AMSI is triggered. But we do need to definitely understand and preface that AMSI is only really used with .NET applications, PowerShell, VBScript, and very few other use cases. It's not every program out there uses AMSI. However, if a program runs PowerShell or WMI or something in the scripting engine world, then AMSI will get loaded and triggered. So that's how it manifests. And then in this graphic from Microsoft's site, you can see sort of the different layers at which AMSI is called. So if you don't use PowerShell directly, it goes down to a COM layer. If you use COM, which is still kind of more in the .NET realm, you can use COM from C++ or C or some other programming language, but COM is going to tie back into the .NET framework since that's where it lives in the Microsoft world. And then if you just bypass COM altogether, and you don't use any of the scripting engines or PowerShell stuff, you're not going to really hit AMSI. You have no tie into anything that AMSI touches, unless there's a third-party AV provider that is doing something to catch what you're doing and then send it over to AMSI and get it scanned, which is what that bottom row kind of represents. So it doesn't tie into all of the Windows API, like I said. But if you're doing anything with PowerShell, which is mainly what we're talking about here, and where sort of the Covenant C2 and other frameworks that are out, open source frameworks out there for pen testing and testing in general, that's sort of where they snag up a lot, is on the AMSI detection stuff. Another sort of thing to keep in mind too, with not necessarily all AV vendors utilize AMSI. Some of them will actually disable AMSI when they run and do their own thing. So something to keep in mind too. And generally, they're not as good as AMSI. So hopefully that's not a practice that'll continue much longer. But it has been definitely seen by a lot of third-party vendors as they just turn off AMSI because they don't use it, they don't need it. So how do we get around AMSI? We have to talk about obfuscation when we talk about AMSI, because that is the biggest way to get around AMSI at this point, other than straight up disabling it, or using some programming language or method, platform, whatever, that doesn't tie into any of the .NET stuff. But if we're going to use PowerShell, or if we're going to use .NET for some reason, or WMI, we have to get around AMSI somehow. We need to trick AMSI into letting us run our code and think it's benign and not malicious. Previously, when AMSI first came out, it was it was less than ideal, because you could pretty much, like going into our example here, you could use this simple obfuscation method, which was just, if you just look at that line and go all the way to the end where it says HTT and then a plus, and then it finishes the URL with another plus in there, that was enough to break AMSI. AMSI couldn't differentiate that there's a plus sign in there, and it couldn't put it back together. So it just said, okay, this looks fine. And then it would let it run. Now, thank goodness, it's much better than that. And we have to move down to like these harder obfuscation methods, which is the bottom sample there, where it's just all this like gobbledygook and a bunch of symbols and decoding and encoding. And some of these methods do still work. And we're actually going to demo this. You guys will be able to try it out in a minute. So obfuscation is not encryption. I made that clear up at the top there. Obfuscation is just hiding and uglifying basically what you're trying to do to trick AMSI, or trick humans, even trick the human eye into not being able to read what you're doing. Again, it's not encryption, because you're not encrypting anything. You can still sort of read at the bottom like what that is. Our human eyes can still read through all the different symbols there and still see. We see download string, we see invoke command, new script block. We can still read it, but AMSI has trouble with that. And that's not even that bad. There's definitely much worse obfuscation than that. Any questions? All right. So here are some open source projects. AMSI fail is definitely one of my favorite too, which we're going to go into. But you can't talk about obfuscation without talking about Daniel Bohannon, who's done a lot of work and a lot of research on AMSI stuff, and wrote the original PowerShell invoke obfuscation commandlet that you can still use and download and play with. And then I only had these three because these were kind of the more common ones. That last one is just like a repo for other research to check out. So I definitely encourage you to look those up. But there are a ton out there, and a lot to read about AMSI bypasses. So without further ado, let's crank up our workstations and try this out. So we have a simple demo setup. Just for sake of time, we're not going to go too in depth here, and I set up most of it for you. So let's go over to Foundry, if you haven't logged in already, and go to the webinar. So you should see this module here. You can hit start to view the content of what we're going to be working on. And then on the side here, you have this little monitor window here, which will slide out and give you your virtual machine. So that's where we're going to be working out of. If you want to work on your own desktop, that's okay. But like I said, I have a lot of stuff set up already, like Covenant set up on the virtual machine already for you. So that'll save you some time. So I'm going to ask you guys to just give me a ping or something when you're ready. Ready? Okay. Okay. All right, Ben or Anthony, are you guys setting up, or you want me to go ahead? Okay, cool. All right, so what we're going to do is open up PowerShell, and we are going to run an AMSI bypass. So in our workstations here, fire it up, and we're going to go to the C tools directory, and then under there we got Covenant and Covenant. So two folders deep. And then I'm going to run the command, and this is all in your lab notes too, by the way. So change directory there, and then we're going to run this command .NET run in that folder. So this is going to take a minute to start up the Covenant console and server and the web app and everything. So we'll let that run, but at the same time, I'm also going to open up another PowerShell terminal just to the side, because I'm going to use that in a second. So we can see here Covenant is running, so I can open up Chrome on my desktop and should pop up in your browser. So going to, and I've already been here, but when you see, if you see that HTTPS warning, the certificate's not valid, just click the advanced button and then proceed to localhost. So the password, username and password are both Covenant all lowercase. And then we can log into the Covenant dashboard. So at this point, we have no grunts, but we're just going to verify that our listener is running. So if we click on the listener tab on the left-hand side, listeners, you should see this HTTP listener, that the status is active. It's listening on localhost on port 80. So the listener is our server, basically, that's going to be waiting for agents to connect and call back in. So that definitely needs to be up and running. And then we're going to, what we need is a grunt running on a host. So a grunt is an agent. It's just what they call, Covenant calls agents is a grunt. So you can, if you click on the grunts panel on the left-hand side, you'll see kind of this dashboard. There's nothing connected right now. So how do we get a grunt running? We go to the launchers tab. So a launcher is a way to install an agent on a host. So if you're in a pen test, obviously this is your targets. You're installing an agent on your targets. If you're testing locally, like AV or some kind of like defense mechanism or heuristic or signature that you just wrote, this is you're going to run this on your lab machine. So when we click on launchers, we can see there's several different types. We're going to go for PowerShell, but you can kind of just read quickly through some different methods you can use to install a grunt on a host. So if we click on the PowerShell launcher, Covenant is smart enough to fill in this information. If you have multiple listeners, you can change your listener here, and change different parameters here. Maybe you don't want it to call back every 5 seconds. You want it to be longer, etc. You can change that. So first thing I'm going to do is generate a grunt, and then it's already generated for you down here, but if you can click it again if you want to, and it's going to spit out these 2 PowerShell scripts at the bottom. The top one is just the default one, and then the bottom one, Covenant tries to sort of pre-base64 encode it for you so that you can kind of paste it in and have a little bit of obfuscation built in already. Little tidbit here, AMSI doesn't care if it's base64 or not, it'll still catch it. So we're going to copy the top one just for an example here, and I'm going to paste it into the screen. If you just hit the right click button in PowerShell, it'll paste it automatically. So once I paste it into my PowerShell command window and hit enter, we get this nice little nastygram. Says this script contains malicious content and it's been blocked by your antivirus software. Thank goodness. AMSI's doing something. So, all right, how do we get around this, right? That's what we're talking about here. So how do we bypass AMSI? So what we're going to do is we're going to use a known bypass from AMSI fail. And you guys can actually do this if you want. AMSI fail, it's .fail. And this is a AMSI bypass generator. So you click the generate button. Every time you hit it, you get a different AMSI bypass. So click around, get whichever one you like. I'll just take this one. No particular order or anything. I'm going to copy that script out. I didn't copy the comment at the top. You can copy it. It doesn't matter. But I'm going to copy that script and paste it right into my PowerShell window. And then I hit enter. So nothing happens. There's no return. There's no kind of dialog message or anything. But it should already have done the bypass that we need. So once I've run that, now I'm just going to hit up arrow to go back to the same command that I was using earlier, but I'm going to do it a little bit differently. Instead of hitting enter right away, I'm going to erase the last quote at the end there, and then I'm going to erase this PowerShell command part and the beginning quote. So it starts with SV and then space O. I don't need the PowerShell stuff. So once that's there, I can hit enter, come back to my Covenant screen, and we see our grunt is activated, and we don't see that antivirus message, right? So it's a little bit nuanced. Maybe, if for the untrained eye, it's easy to not understand necessarily what happened there, but I'll go over that in a second. So if I go back to my grunt tab, I can see that my grunt has connected. Since I'm running as administrator, this is a really nice high quality grunt. So I can come in here, I can do who am I, run some commands on my grunt. And now basically my Covenant server is talking to the agent on the host, right? You can imagine in a normal situation where this is happening, either in a pen test or in an actual attack scenario, my Covenant server is not going to be on the same machine. It's going to be hosted somewhere, AWS or Microsoft or somewhere, and then the agent is going to be talking to the cloud and talking back to my server. So I basically have now control over this machine. We can see it returned my administrator account. If you click on tasks, you can see a bunch of different tasks that are here. So just another example, another example here that we can run is, and Covenant has a really cool autocomplete feature too, so you can see what the different commands are before you type them. So what if we run Mimikatz, and we try to dump some secrets. Let's see what happens. Ooh, okay, so we get a compilation error and it said it couldn't find the file. So what that's telling me is that the agent tried to download the file and Defender or the AV, whatever AV is on the system, deleted that file. So two things just happened. Either hopefully I didn't get caught because the Defender just triggered and sent out an alert. But we also just logged, this file called powercats86.dll. And now we're sort of giving ourselves away. So, but why did this happen, right? So first of all, Defender already has a signature for Mimikatz. Mimikatz is definitely a widely used, heavily used tool by not just pen testers, but malicious folks as well. So there's a lot of incentive out there to catch Mimikatz quick and fast before it runs and dumps the passwords of a system. So what else can we do while we have this PowerShell session? Because there's definitely some gotchas that I'm going to get into here. So we can still, our grunt isn't dead. It only, Defender only killed the Mimikatz DLL. It didn't kill our process. So we can still work. We can still do stuff. We can still have control over this PowerShell session. The gotcha here is that when we did this AMSI bypass, we did it locally to this PowerShell instance. So I have a graphic to pull up there to give you an example. Does anyone have questions really quick before we move on? Covenant is awesome. Like I said, I'm not going to go too much into Covenant in this talk because this is more about AMSI and AV detection stuff, but you can sort of imagine and browse through the tasks to see all of the cool stuff you can do with Covenant as long as you can get it running. And that's sort of the tricky part. That's the frustrating part. You can run other binaries, other executables. You don't have to run PowerShell. You're not stuck in PowerShell land with Covenant. You can basically run any command you like. So it's definitely, I'm not doing it justice here with this demo, but there's a lot more you can do with it. So if we go back to my slides here, let's talk about how this bypass worked. Threw me all the way to the beginning. Okay, so how did our AMSI bypass work? So I flipped through, when I clicked on the generate button, I flipped through a bunch of different bypass techniques and variations of them. But they all generally kind of work the same way. There's a few variations, minor, just kind of nuances on how they work, but this is the gist of it. Our process on the left-hand side, my process.exe, was my PowerShell terminal. When we run our AMSI bypass patch, we're finding the AMSI DLL that's locally in our process that Windows put there. We didn't put it there, but because of, like we talked about, the stack of tools that we're using, like PowerShell, VB scripts, .NET stuff, all of those processes already have an AMSI DLL in them, placed there by Microsoft. And that's how it triggers the AMSI functions to run, because it has that local AMSI inside the process already. So what we do when we run our AMSI bypass patch is we locate that DLL locally in our own process. Again, this isn't like the Windows copy. We're not affecting any other process. We're only affecting our own process. We go to that DLL and we find this AMSI scan buffer function that's on the right-hand side. And then we do our Jedi mind trick and say, anything I send you is okay. So we basically patch the AMSI DLL in our own process and say, anytime you get a script, just return true. Everything's okay. AMSI DLL doesn't know any better. It doesn't have any smarts. It's just a DLL. So it doesn't really have a defense against this. And since we own this process, we are the creators of this process, that means we also have access to the DLL within our own process. So we don't have to, you know, escalate our privileges to do this. We don't have to talk to any APIs. There, you do have to talk to APIs. You have to call certain functions to do it, but I'm saying you don't have to like have administrative control over anything. And then once that's done, this process now is completely free and clear to run any sort of PowerShell script or VB script or any script that was previously being detected by AMSI. So what are the other gotchas that I mentioned earlier? If my process.exe launches another process, especially another PowerShell process, we would have to now patch that other process before we can do anything malicious in it that would get caught. If it's a normal benign like PowerShell command, it's fine. Nothing, there's no problem there. But if we're trying to run another grunt, or we're trying to run Mimikatz, or trying to do something else in memory, then we'll have to patch it before we can do anything, if that makes sense. So this also kind of holds true to, well, we saw like the example with Mimikatz. If we download a file, we have to make sure that file is not going to get caught or picked up by a defender. So that usually entails either recompiling or changing things up to defeat the signatures. And then we can sort of pivot over to that executable instead of running in the PowerShell. Because obviously it's frustrating and tedious to have to remember and deal with bypassing AMSI every time you start up a new process. You have to write your scripts in a certain way to have your bypass run first and then your subsequent script. So ideally, kind of Covenant in this case would be sort of your stage one kind of you can set up persistence with Covenant. So we would set like a run key or some auto run or something with our Covenant our grunt, have it bypass and then run Covenant. And then once we have the need to connect to this machine, we can just go to the Covenant dashboard, go into the task console, drop down some other binary that we can use for, more powerful control over the machine, I guess you could say. So maybe it does specific things that we need it to do that Covenant doesn't necessarily do. So that's pretty much the long and short of it. I'm happy to go into more detail if anybody has questions about that stuff. But yeah, does anybody have any questions in general?
Excuse me. Yeah, I have a question about the .NET version. So with Covenant, you can target 3.5 or 4.0.
Yes.
Now, when you actually run that, let's say the target that you're running it on has like 4.7 installed, and you compile for 4.0. Now, 4.7, I think, or it might be 4.8. One of them like has support for AMSI. When you run that binary targeted at 4.0, would that run without those additional features that are available in the installed version, the higher, or is it like, or does Windows say like, oh, well, this was targeted at 4.0, I'll only run it with features that we had with at 4.0?
No, so it'll run with whatever version is installed, on the machine, not what you compiled it for. And you also have to be careful too, because if you compile it for like 4.8 and you try to run it on an older system that doesn't have 4.8 on it, you're gonna get a pop-up that says you need .NET 4.8 to run this, right? Gotcha. So those are the differences with the versions. But yeah, it's gonna whatever's installed on, and this isn't even about Covenant. This is just like normal software development when you're developing applications natively. That's definitely something you have to be aware of, is what version does the customer have installed. You can even update it yourself if you wanted to, have the installer run the .NET updater and pull it up to the version that you want to. But yeah, and AMSI is going to run basically on a Windows 10 system. It doesn't matter what .NET version you have installed. AMSI is still going to run the same across the board. It kind of has that independent thing to it. But obviously, if somebody hasn't patched in a while and they have like an older AMSI version, then it's not going to get the latest updates. So if Covenant was getting caught, is getting caught now, and it wasn't getting caught a year ago, and somebody just has like a really old version, you're in the clear.
Does that apply to 3.5 as well? Because I know they target two different, strictly
Yeah,
for AMZ and bypass and C sharp. Because the 3.5 I think targets 2.0 for the CLR, and
correct.
4 I think targets 4.
It definitely has it has more limited feature sets on 3.5 and way back to 2 obviously. AMZ ports back to Windows 8. It doesn't do anything on Windows 7 because it doesn't exist there, and it doesn't have the the newer runtimes and stuff to tie into. So if you have Windows 7, you don't have to worry too much about AMZ. And if you do, it's like a very limited subset of AMZ. I don't even think you can install it. I'll have to double check that, but I don't think AMZ can even run on Windows 7. But Windows 7 is end of life anyway, so it's not a big deal. Um, Windows Server is a little bit more hit or miss. Our demo and the VM that we had set up here is a Windows Server 2019 box, but generally, what a lot of people are going to do in an enterprise setting, and I don't know, maybe this isn't a lot of people, but there's going to be a good chunk of people out there that will disable Defender and AMZ on a server machine just for like resources and that kind of reason, not necessarily because they just want to leave everything vulnerable, or they'll have some other EDR solution or some other monitoring solution to monitor specific, especially critical servers. So, that's good for us. That's bad for them. But that's another thing to keep in mind. Servers kind of run it less than normal. And enterprise solutions too, or enterprise environments, it's kind of hit or miss still these days of people that are actually running AMZ and running Defender. So you might not even have to deal with it a lot of times.
Do you think over the next 3 to 4 years? I mean, I would say like .NET is picked up pretty heavily in the past 2 or 3 years. Do you think over the next 3 or 4 years, tools like Golang, which has like a built-in runtime in its own in the binary, or Rust, will have greater success at bypassing some of these native protections, or does that not really matter? I guess.
I mean, right now, Golang, Rust, Python, they don't tie into AMZ at all. So there's talks about potentially changing that, especially Python, because it's a scripting language. It could be monitored like PowerShell and the other .NET stuff, but it's not. You have to kind of rely on third-party vendors to set up rules to scan at least Python. Rust and Golang are different because they're going to compile down to native code. So it's basically like you're writing a C application. AMZ doesn't touch that low-level stuff. It can't, right? It's looking at binaries. But if your binary, again, like we talked about here in the demo, if your binary calls PowerShell or does some WMI call or does some other .NET or COM reach over into that world, then you're getting into AMZ again. So it's stuff you still have to be careful of. You can still do the same tricks in the binary. When you start up your binary, you can disable AMZ before anything else runs, and then you can run all your PowerShell commands just fine locally, and AMZ won't touch it.
Cool. Thanks.
Yeah, no problem, man. Good questions, Jim. Anybody else? We wrapped up kind of quickly here today, but I'll give you guys the rest of your time back. I'll hang around if you have any questions, but thanks for joining us. We're going to keep doing these kinds of sessions in the future. So, please join. And yeah, thanks. All right. You guys have a good day.